Welcome to another podcast. In this video, we're going to be taking a look at a concept called the radius of convergence of a power series. This is one of the more important topics that we'll discuss for the remainder of the semester, especially because it has the opportunity to impact us in almost every topic we'll look at between now and the end of school. Also, it's one of those topics that will occur frequently in all of the math classes that you would take after this one. So this is definitely a topic that you want to give your full attention to. So given a power series, so we have the center point at x0. Given a power series, there's three things that can happen. The series might converge only at the center point. So that is always true. You always get convergence at the center. Always converges at the center. And the reason is, if you think back to the animation I had in the previous video, we started off by looking at a line that passes through the center point. And every line from then on, or every curve from then on, uses that as an anchor. And so nothing moves off the center point. So the two functions, the function and the polynomial representation, they always share the center point as a common element. So you always get convergence at the center. It's just as soon as you move off that point, how good is your approximation? Well, you might get a function for which the series converges for all x, and these have a name. If you have a function that satisfies b, the function is called an analytic function. These are incredibly important. We'll talk about a couple of them coming up when we look at some power series representations, but analytic functions are functions whose power series representations converge for all x. And then the majority of times what happens is you get C. And so C is the one that we're going to devote most of our attention to. Sometimes you can have a power series that only converges for an interval. And so if that interval is a distance of r on either side of the center point, then you say that your radius of convergence is r. If you get outside the center point, then you're going to diverge, and sometimes we'll need to check at the endpoints. The best way to talk about this is probably with a small demonstration or a picture kind of what is going on. So just consider here for a second that we have a sum, and our center point is at the point x naught. Then saying that the absolute value of x minus x naught is less than r, that's the same thing as saying that x minus x naught is less than r, but it's also greater than negative r. And so you can see here that if I subtract x naught, or add x naught to all those pieces, I get, let's see, x naught minus, so if I add it over here, I get x naught minus r is less than x naught plus r. This just says that I can go up to a distance of r away from the center point, and that's called my radius of convergence. It makes sense to call it a radius, given that it's the half distance here on either ends. And what ends up happening is on my radius of convergence, on this interval called the interval of convergence, the representation works, and oftentimes I'll need to go in and check specifically, do I get convergence at these endpoints? So I'll have to specifically check the endpoints for convergence. But if I know r is my radius of convergence, then I know that I get convergence up until the point x naught plus r, x naught minus r on my interval of convergence, and I might have to check the endpoints. A good example of this is previously we said that the function 1 over 1 minus x, that function has a power series representation given by this, and this is valid for the absolute value of x less than 1. Well, if you compare this with this notation here, then it becomes clear that R is 1 and the center point is 0. And so your interval of convergence is from -1 to 1. And we've discussed in class that you can't include the point. This would be the point 1. This would be the point -1. The center point would be 0 in that case. You can't include either of the two endpoints for this function because you don't get convergence there. You can clearly see if you try to plug 1 into the function anyway, it's discontinuous at the point 1. So that's not going to work. And it turns out that -1 doesn't work either. So just as sort of a small example of how to perform this process, I want to take a look at a different sum. So suppose we're looking at the sum n goes from 0 to infinity of x to the n over n squared. And so what I want to do here is I want to find the radius of convergence for this power series. Now, the radius of convergence is only important if I know its function representation. So we're going to have to eventually figure out what is the function that this is representing, but we can find the radius of convergence without knowing that. In order to do this, you have to apply the ratio test. So if I use the ratio test, then remember the way that that works. The ratio test is the limit as n goes to infinity of an plus 1 over an, which in this case is the limit n goes to infinity of, you get x to the n plus 1 over n plus 1 squared times, remember you take the reciprocal of the function. And so if we get some cancellations to occur here, we get x to the n cancels with x to the n plus 1, leaving just one copy of x. And then we've got n squared over n plus 1 squared. So this would be, let's see here, the limit as n goes to infinity of the absolute value of n squared over n plus 1 squared times x. So if I look at taking the limit as n goes to infinity of this, because this term is rational with the numerator power equal to the denominator power, then it's the ratio of the leading coefficients, so the limit of this is going to be equal to 1. And so all that leaves is the absolute value of 1 times x, or just the absolute value of x. And so the limit here depends on x, as we would expect. This is why it's different than the sequences stuff, or than the infinite series convergence test, just the standard ratio test that we were using previously. Is we have x involved now. And so the value of x can be anything, but in order for this to converge, the ratio test says that what comes out of this process has to be less than 1. And so that tells me right there that my radius of convergence is going to be 1. And my interval of convergence is going to be at least -1 to 1, because, going back to this whole interval idea, this series is centered at the point x not equal to 0. You can see that the center point is 0. The radius is 1, so I'm going out to 1 and -1. I'm going 1 in either direction. And now I have to check for convergence at either endpoint. Now the way that you check for convergence, so I'm going to check the endpoints here. The way that you do that is by taking the original sum and plugging in the endpoint. So if I plug in x equal to 1 into the sum, this now becomes the sum from 0 to infinity of 1 to the n is just 1 over n squared. And we know that 1 over n squared converges. It's less than infinity because it's a p series with p equal to 2. So the idea is, at the point 1, it's not a question anymore. I know I get convergence. So I can check off 1. I get convergence there. What about the point -1? Well, if I plug in -1, then I'm looking at this series, and we know that this series is also less than infinity because it converges by the alternating series test. Remember, the alternating series test says if you have an alternating series such as this one, then if the limit as n goes to infinity of the absolute value of that series, which is 1 over n squared, if that goes to 0, which it does, then it converges. And so there's no longer a question mark at the left endpoint. I can check it off, and we're good there. And so the point is, my interval of convergence, it's not an open interval anymore. I can actually close it now and say that my interval of convergence includes both endpoints. And so what our final answer here is that the radius of convergence is 1, and the interval of convergence is from -1 to 1, including both endpoints. And so this is sort of the process that we're going to go through to figure out radius of convergence and interval of convergence. I'm going to look at one more example of this with you, maybe a slightly tougher example. But this is the basic idea behind this problem. All right, thank you for watching.